Our last segment of the day is a keynote talk sponsored by KBR, so let's hear a quick word from them. And with that, to introduce our keynote speaker, I'd like to welcome up Jeff Wozniak, Chief Space Systems Engineer at KBR. Jeff.
Thank you. Thanks, Jim, and hello. KBR is a proud sponsor of the first keynote speaker at this year's Goddard Memorial Symposium. KBR is a space company. From the design and deployment of the James Webb Space Telescope and flying the International Space Station to training astronauts and range support at Wallops. Our thousands of experts and employees work on the most complex space projects, including the Dragonfly here at APL, and for nearly 60 years, multiple Earth and space missions at the Goddard Space Flight Center. KBR's support of NASA, the nation, and commercial space spans all areas of engineering, operations, and science to enable a plethora of current and future missions. At KBR, we're proud to work with our customers here and across the globe to provide pioneering technology and value-added service for our customers. Tonight, it is our honor to introduce Dr. Christa Peters-Lidard. Dr. Peters-Lidard is the Director of the Sciences and Exploration Directorate at the Goddard Space Flight Center and has been at the center since 2001, serving in a variety of leadership roles. Among her many honors, she was recently elected to the National Academy of Engineering. Her research interests include land-atmosphere interactions and soil moisture measurement and modeling, and the application of high-performance computing and communication technologies in Earth system modeling. Her PhD is from Princeton University, and she holds a BS in geophysics from Virginia Tech. She is passionate about Famine Early Warning System Network and is excited about the growth in Earth's remote sensing sources that will revolutionize our ability to better protect our planet. Dr. Peters-Lidard, everyone.
All right. All right, thank you very much. Yes, it's working great. All right, I decided to use the remote mic so I could move around because I like to move around. So I am here today to stand between you and the reception. So we have about 20 minutes. So let me make sure I get you there on time. So I am so excited to talk about this idea. This is a vision that I've been thinking about for a while, and I want to put it out there to the world, and that is NASA and our partners are uniquely poised to build a digital twin universe, right? So this symposium is about our environment in space, and what you've heard today is that we do a lot of measurements and we have a lot of models, right? And so how many of you have heard of a digital twin? Everybody? Yes, almost everyone. So a digital twin is basically, it's used a lot in engineering, right? So it's like a digital twin of a satellite or a digital twin of a spacecraft or an airplane. Well, there's also digital twins of planets. There's digital twins of our solar system, and there's digital twins of exoplanets in other solar systems and other galaxies. So I think this is one way we can pull all of our assets together and look towards the future as we move into our new space. So, it's not advancing. There it is. Oh, back one. All right, there we go. Okay, so you heard about this earlier today. So why do we want to have a digital twin of our magnetosphere and our Earth environment? Well, last year, almost a year ago, SpaceX lost about 40 of its Starlink satellites. And why did that happen? You heard earlier today that it was sort of a moderate event, right? It wasn't one that, like alarms were not sounding, but yet this event impacted this system in ways we didn't understand. And so maybe we needed a whole atmosphere model to really understand the impacts of a moderate event on the drag for these spacecraft. And as we move, we just heard about our exploration moving, we're moving back to the moon and eventually on to Mars. And we need situational awareness. We're not just protecting space-based assets, we're protecting humans. So we need to be able to understand, model, and predict, based on the latest data, what is happening with solar energetic particle fluxes, and we need to be able to warn people, right? So we need to have the capability to adapt our digital twins based on constantly updating them with data, right? That is the key to being able to have space situational awareness and to protect all of our assets. So the backbone of this system is our observation fleet, right? So the different colors here represent different sciences. So blue is earth science, and then you'll see, red for astrophysics. And, we've got a lot of assets in low Earth orbit, right? But we also have assets that are at GEO. We're out at L1. And so this entire architecture is the foundation for how we can observe constantly throughout our solar system and beyond. But that's not our only data, right? So we've been doing digital twins in earth science for decades. We just didn't call them that. We basically take models based on physics, and we assimilate data from stations on the ground, from aircraft. So you can see in this, you see all the yellow over the US, that's aircraft. We use that data in our models. That's part of the digital twin. And there are millions of observations assimilated every day into our models, into our weather models, and we do this at Goddard as well. This is an example of the data we assimilate now into our GEOS model, which is a global Earth observing system model. And all of these pieces, from satellites, from the ground, from aircraft, are put together so that we now have constantly updated representations of our, and what did Dahlia say? The land, she had a great expression now, I forgot. Anyway, surf turf, yes, and above the earth. That's it, surf turf above the earth. So that's what we do. So here's an example. This is one of my favorite examples. This is a project that I worked on for many years, the Global Precipitation Measurement Mission. And so in the middle of that was a satellite called the GPM Core, launched with our partners at JAXA. Highly calibrated radiometer that then is used to calibrate all these other satellites and produce a map of precipitation that is updated in real time. Check out the dates. That's from this week. Okay, so this is something we do today in real time at NASA. This is our iMerge product. It produces data every 30 minutes on a 10-kilometer grid. It's like having radars everywhere in the world, okay? And the blue and purpley colors are the snow and frozen precipitation. So, the other things we've been doing for years is we've been monitoring our climate, right? So, I mean, a digital twin of our Earth is certainly, we want to go back in time, and then we want to look at how that's changing over time. So this is climate data from our Goddard Institute for Space Studies. This is our GIS-TEMP product that shows how the world is warming. And it's unmistakable. This is, we put this together from all of these data sets worldwide. But now what we're able to do is something amazing. So we've been doing data analysis for many years. This just came out this week in Nature on the cover. We are using commercial satellite data, actually it's the Digital Globe, the Maxar Digital Globe product, to count trees, first of all, counting trees, and then assessing how much carbon is stored in the trees. So we are now counting carbon in this region, okay? And so if you can count carbon in this region, now you can start counting carbon everywhere. And so your digital twin will now include water and carbon, not just weather. This is where we're going. So now let's take our earth science examples and expand on it a little bit more. So what are you looking at here? This is from our model. This is the digital twin of the atmosphere showing aerosols. Aerosols are these small particles. You can see the smoke. So we put fire into this model, and then it emits smoke, and the smoke gets transported. So that's the white, is the smoke. You can see the dust coming off of the Sahara. So that's another color. And then the blue is the sea salt. So all of these aerosols are modeled today. This is our Earth digital twin. Okay, and then finally, the greenhouse gas. And so we have CO2. This is carbon dioxide. Again, you can see every day, so the dates are there. Every day there's a pulse, right? Because trees or plants absorb CO2 in the day and they emit it at night. So there's a constant pulsing, but there's also other emissions of CO2. All of that gets put into the model based on data. And so what you're seeing now is the model is resolving the entire atmosphere. So we're tilting it so you can see how what comes out at the ground gets mixed up into the atmosphere. So we can do all this today. This is happening now at Goddard in the GMAO. And we work with our partners at NOAA to, some of the same techniques that we use in these models are being used at NOAA as well. So what's really amazing, though, is that you start to understand how interconnected our systems are. And so this is just one little example, which just came out in a paper, where it turns out that if you look at the upper atmosphere, even though greenhouse gases are warming the lower parts of the atmosphere, they're actually cooling at the top of the atmosphere. And that cooling produces a shrinkage. So meteors are burning up at lower altitudes now because of greenhouse gas and climate change. And you can see this. So it's all connected. Our environment is connected. This one blew my mind. I was like, what? We're using meteors? I mean, you can measure the cooling with the meteors. Anyway, so let's talk about the other key part of our solar system, our sun, right? So we observe this with our Solar Dynamics Observatory. We have we have SOHO, we have ACE, we have our GOES system. I mean, we're looking at many different aspects of the sun, stereo as well. And what we're now trying to do is develop models that can predict when a large coronal mass ejection happens, as shown here. And so if you can understand, and when Parker comes close, I mean, that's more data, right? We're really trying to understand the physics of the sun. And so that will become our digital twin of the sun, based on the data and the models. So now we have weather models. Our CCMC team and other, our collaboration with SWPC, you heard a great panel earlier today about this. This particular event, we got lucky because Earth is over there. You're looking at the solar system. The event that you're going to see, boom, it goes past stereo A, but not Earth. But this was, we just got lucky. It was, things were facing in a direction that wasn't facing Earth. But again, the models, so in this case, you have to have a model to understand, the source, and then you have to propagate this event through the solar system. So this is from the Enlil model. And then you have to then assess the impact of that in the environment of not just Earth, but now the Moon and Mars and everywhere where we're going to be in the solar system. So, you know, there's folks working on really cool, like, you know, new physics and new approximations to these models. So I think we can't forget that to have a good digital twin, you need to develop the models to actually represent reality. And that is still a need that we have. So I think, you know, as we learn about the physics and we develop better models, we get better space weather. So here's another little interesting one. So, you know, this is all part of our understanding of the interconnected nature of our solar system and our in this case, you know, you've all heard about the moon and ocean tides, right? But actually the moon also does atmospheric tides. There's actually, the atmosphere actually responds to the moon. And so in this particular paper that was published, you know, you actually need to understand these tides to properly model the ionosphere and the thermosphere when you're, so then again, feeding back into these whole atmosphere models and ultimately understanding impacts potentially from space weather or for other, on other assets in orbit. So we've got to understand our, you know, the heliosphere, we've got to understand our magnetosphere, we've got to understand the moon. So we need to have a lunar digital twin too, right? We just heard a lot of interesting discussion about resources. So our lunar reconnaissance orbiter has, you know, been orbiting for a long time. That's kind of the backbone of our understanding. We've got digital elevation models with USGS. We have the basics of this, and now we're starting to think about, well, where are the resources? And you know, we can look for resources, but again, we have to be careful about, you know, how we use them, whether we use them. I think that's a different question, but I think the models will tell us how much is there, and they will be constrained by the data from CLIPS and other newer observations that come online. So again, you know, we now observe in the, you know, the Mars environment, we've got simulations to look at, you know, the solar wind and how it stripped, you know, go back in the past and try to simulate how Mars' atmosphere was stripped away. And I think we're still going to be monitoring, you know, the environment, because those solar energetic particles, as they arrive, this is a very weak magnetic field, but you know, how that interaction occurs and then being able to predict it at the surface where the assets are, that's where we need to be. So again, we need to have models of the atmosphere, the surface, and the magnetospheres of all of our, you know, places of interest. So now we can think about moving outside of our solar system. We used to think there weren't that many exoplanets, but TESS has shown us that that's not true. TESS has shown us that there's over 5,000, and that's just at the end of last year. They're everywhere. Okay, so now we know where to look, and for every exoplanet, you can imagine, as we start exploring it, we're going to need a model. But before we do that, we look at the exoplanets of interest, which is what JWST is doing now, right? So we take the TESS survey, we start to look at planets that we think are, you know, potential candidates in the habitable zone, and you start to find water vapor. And so this has already been done with JWST. And so now what you can do is you can have a planet, in this case Proxima b, where we actually took a model that was developed for Earth for climate simulations called Rocky 3D, and we can model the climate of this exoplanet. So we now have, this already exists, this is a digital twin of this exoplanet based on very limited observations. Proxima b is actually very hard to observe, so that's another conversation. But the bottom line is you can assume that there might be an ocean there. And if there's an ocean and some continents, and depending on, in this case, Proxima b is it's gravitationally locked with its star. So as it rotates, there's always one side facing. So to get heat from the sun-facing side to the non-sun-facing side, you might require an ocean to have currents that can transport the heat on the other dark side of a planet like that. So we have models now that can do this. So this is, an example of that. So if you think about the future and where we're going, right? We're going to have spectroscopy of these exoplanets. We've got models, and we're going to be able to potentially, model all these exoplanets. The last example I want to show is, a data-driven animation. So again, like a digital twin is just based on data. This is actually based on data that was collected before OSIRIS-REx landed on Bennu. We circled it and took a lot of data. So we had super high resolution data. And when it took its sample, there was so much debris blown out, we actually measured the topography afterwards. So we did a flyby after the sample was collected, and we were able to estimate the depth of the crater caused by the sample extraction. So that's what this is. So the colors actually represent the depth, the height change in centimeters. And you can see marks from the thrusters. So we were just talking about that in the previous panel, with the lunar thrusters. We did it on Bennu, on an asteroid, with super high resolution models. So we're there. So I think this is just, it's all possible. The pieces are there. So looking forward in time, Dragonfly, here we are, APL. Titan, we're gonna have amazing data on Titan after Dragonfly. So we're gonna have the capability to do the same thing. And then of course, Da Vinci, going to Venus, flying through the atmosphere, and then ultimately to the surface. Really lots of questions about the Venusian atmosphere and its composition. So, I think we're in an amazing time right now, and we are going to be able to characterize our universe in a way we've never been able to do. And with Roman Space Telescope, there's Hubble, the little section that we saw with Hubble versus what we're going to see with Roman. It's amazing. 200 times the field of view. Our eyes are going to be open wide. So, and then of course, as we move forward in time, the habitable worlds, that's the next great observatory, right? So we're going to have these models. We're going to have already studied this spectroscopy, and now we're really going to understand and look for life out there. So let me end it there. I think, our decadal surveys drive a lot of what we do. But I think this idea of a digital twin universe can tie it all together, because all of these separate activities are actually interconnected. And so I think that's the one message I want to leave you with tonight before we break, is that, the potential is huge. This is the year of open science. It's a heliophysics big year. We're doing, lunar landings. There's so much happening. And the data is going to be amazing. And so let's use it and put it all together to understand our universe. That's it. Thank you.
Thank you very much. Would you like to take any questions, if anybody has any? Any questions for Dr. Peters-Lidard, or is it?
Or I can take questions during the reception.
Right. So yeah, one question right there.
So yeah.
Okay.
Feel free. Yeah.
The start of a digital twin, and can we just add the NASA data to it?
Oh yeah. So you can, and I think, to me, Google Earth is like a great portal to data. But the difference here is that the foundational science and the sort of meat behind it is what I'm talking about, right? So the you could certainly use that as the tippy top of your portal to access the data. And there's Google Mars. I mean, there's already, a lot of that exists. So I think there's lots of creative people here. We've got our students here. You want y'all think about how you want to do this? So I think you can imagine many ways to access the data. Putting it all together, though, in a science context is important, and so we need to make sure that we don't lose that. I think it's a partnership.
Thank you.
Yeah.
Excellent. All right. Well, thank you again
All right.
so much.
Thank you.